Now, here is, how much time do I have, or did I already pass the time? Half an hour? Okay, this I understand. Okay. Here is an anecdote. In 1986, we sat down together again at NBS. Every summer I was there with a group of friends, and one of us brought from his office a drawing, which I confiscated later on, and this is the drawing he made by hand. He did a calculation of the number of pages in the bibliography, which is n, but this is 1 over n. So this is the number of pages in the bibliography. So each page contains maybe 20, 30 papers, right? This is the number of pages in the bibliography. And this is the date, 1986, January, February, and so on. So he started in, I don't know, in May, or he started before, in April, and he drew these numbers and continued this. And to our horror, it was clear to us that in December of 1986, the number of publications on quasi-periodic materials will reach infinity. And here is the scientific proof, right? And all the forests of the Amazon will have to be cut just to print all these papers. Well, it didn't happen. But this was the feeling that the world is really exploding. I will now go very quickly and show you just one thing which is scientific, and then answer one question that I will ask, and I will finish, okay? And that thing is, that method is a mathematical method which is called the cut and projection method, cut and project, and this is so beautiful I have to show you. I was shown this method, which the mathematicians knew before, in 1985 in Paris, in the High School of Chemistry, High School of Mathematics, and this is what it is. So what we do here is the following. You take a periodic array in a high-dimensional space. In this case, you have a periodic array in a 2-dimensional space. And what you do with it is you make a cut. And here is the cut that I have made. You made a strip. You start with an atom here and made a strip. But this direction of the strip, this tangent, is not just any tangent. Alpha, tangent of alpha, is the Fibonacci number tau, which is 1 plus root phi divided by 2, and it is an irrational number. When I say that the direction is an irrational number, it means that if I start with a point here, then this line will never meet any point, ever. Because if it does meet any point, then the tangent becomes a rational number, not an irrational number. But I chose the direction of an irrational number. It can never meet any point. What you do next is you project on the line all the lattice points that are within the strip. And now you look at the distances that are formed on this line. So we have a long distance, and a short distance, long, short, long, short, long, long, short, and so on and so forth. This is a quasi-periodic array in 1 dimension, like the Fibonacci series, 1, 2, 3, 5, and so on. So this is the way to take a higher dimensional space, cut and project. The higher dimensional space is periodic, cut and project, and receive a quasi-periodic, a non-periodic array. So now, if you have some time in the evening, you can take a 6-dimensional space, cut and project it onto a 3-dimensional space, and if you choose a periodic 6-dimensional space, cut and project, you'll get a 3-dimensional quasi-periodic space, which some of these exist, but you can predict what others can possibly exist. Do they exist? We don't know. So this is the beautiful cut and projection. Now let me show you something else. This is what I had before. Now I take another direction, very close. Look at the red lines, very close to the black line. But this one is periodic. I chose it to be periodic, so it will meet, the red line meets this spot. So the tangent is 11 divided by 7, and which is 1.5714, but it is periodic. So what is the periodicity? It's a large periodicity from this point to this point, and then more and more and more. Very large motif that repeats itself. The crystals that are based on that are called approximants, and they're called approximants because they are approximately quasi-periodic. And such crystals exist, hundreds of them exist. Okay, enough of them. We shall skip all the theory about quasi-periodicity for sake of time. I just want to show you the last couple slides. While as before, order was synonym with periodicity. Periodicity is order, order is periodicity in crystals. Now we know that order can be either periodic or quasi-periodic. And this arrow marks a paradigm shift. This is the most important outcome of the discovery, a paradigm shift in crystallography. Now, let me ask you the question and answer it. Why quasi-periodic materials were never discovered before 1982? You see, for 70 years, eminent crystallographers studied hundreds of thousands of crystals around the world, and nobody saw ever a quasi-periodic crystal? Is it because they are very rare? Maybe they are not stable? They transform quickly, you raise the temperature to 10 degrees C and they transform to a periodic structure, or maybe they are difficult to make, or maybe they are made of very exotic elements that nobody studies, praseodymium, gadolinium, and some copper in the corner will create that. Well, let's see the answers. Number one, are they rare? Oh, not at all. You see, there are hundreds upon hundreds of quasi-periodic materials. This list is a partial list of the quasi-periodic materials based on aluminum alone. And there are quasi-periodic materials based on other elements, many other elements. So there are hundreds upon hundreds of them. No, this is not the answer. It's not that they were not discovered because they are rare. They're not rare at all. Maybe they're not stable. Well, many of them are not stable. What does it mean? It means that if you heat them up to 350, 400 degrees C, then they will transform. But at room temperature, they're very stable. And then there are other alloys that melt congruently and they are stable, always stable. Or maybe they're difficult to make. Oh, not at all. They're very easy to make. You can cast them, you can rapidly solidify them, you do single crystal growth, you can do electrodeposition, CVD, PVD, you can create, in any method that you can create other materials, you can create quasi-periodic materials. Are they made of very expensive materials, very rare elements? No. We talk aluminum, manganese, iron, copper, everywhere. Magnesium, zirconium, it's everywhere. No. These are not the answer. Let me give you my answer, and from here on, it's not objective. It's subjective. That's my opinion. Why is it that they were not discovered for so many years? Number one, TEM, transmission electron microscope. Quasi-periodic materials had to be discovered by a transmission electron microscope. There was no other way to discover them. Why so? Because if you happen to have a material which is quasi-periodic in your hand, and you did X-ray diffraction, you lose the rotation symmetry because many crystals are oriented in different directions. So you don't see the five-fold rotation symmetry. So you cannot discover it. You just say, oh, this is a very complicated structure. And if you look at the phase diagrams, many times they say, this phase, complicated structure. But in fact, it's very simple, only it's quasi-periodic. It's not periodic. So TM. And when you do TM, you need to be a professional. And it's me? Maybe. No. Anyway, you have to be a professional. And this is my message to young people. If you want to succeed in anything you want to do in your life, be a professional and start now. Start being a professional now. Find a subject that interests you, and today information is available everywhere. Start being a professional now. If you want to change later, change, but then become a professional in another subject. And you know what I say to young people? Today, not only you can find many things on the internet, in books, everywhere, you can also call a professor in university who is the world expert in the subject and ask him a question, and you know what? He will talk to you. We talk to young people. We like it. We like young people to call us. So be a professional. A professional in electron microscopy does not mean one which knows how to operate the microscope. One that operates the microscope has a driver's license on the microscope, means that the man responsible for the microscope knows that he will not destroy the microscope. But it doesn't mean that he knows what to do with it. And most students who do electron microscopy use it as a very nice magnifying glass. They get pictures with high magnification, show it to the professor, who is usually not an expert in the subject. Professor says, wow, wonderful. So give me 5 more for the thesis, and that will be it. So very few electron microscopists become professionals, and I was a professional in electron microscopy. And then once you discover it, you have to have tenacity. Rottweiler, you bite and you don't let go. Even if people tell you that this cannot be, you just continue with your beliefs. And let me tell you about myself. I am the worst critic of myself. And when I convince myself that what I'm saying is right, then somebody has to come with experimental results to show me that I'm right. Not with a theory which I know from day one cannot be. No. I'm open to talk. I'm open to listen. But nobody came with anything contradicting my experimental results. So you have to have tenacity. And 2 more things. You have to believe in yourself. How do you believe in yourself? Well, make sure your mother loves you when you're very young. That helps. And also make sure your father loves you when you're very young. That helps too. But self-confidence is something that you grow up with, and then you can stand tall against opposition. And the last thing is courage. I was young at the early stages of my academic career. There were quite a few people who objected my promotions and went to line. One of them went to Linus Pauling, and he wrote a letter to the provost of Technion saying, hey, Danny Schachtman is talking nonsense. And this is Linus Pauling says. Now, I'm not saying that, but Linus Pauling the Great says that. Are you going to promote this person? Are you going to let him become an associate professor? Okay. So you have to have some courage. But let me tell you one last thing. One person, at least one person, saw that 5-fold rotational symmetry diffraction pattern before me. How do I know that? Because he was a student in Belgium, and his professor told me that. His professor looked through the files of the slides from previous years and found my diffraction pattern that was discovered by somebody else, by one of his students, years before me. So he calls his student and say, you know that you saw Danny Schachtman results years before him? He said, yep, I know. He said, why didn't you show me? He said, Professor, if I would show you, you would want me to stay 2 more years in my PhD, right? He said, yes. He said, no, I wanted my PhD, thank you very much. So you have to have some tenacity. And thank you very much.